Okay, so we have our first talk for the session. It's, sorry, I got to say you Zhao Yu Yang. I saw quadruple points. This must be someone associated with wrong.
Should we start now?
Yes.
Okay.
Yeah.
Hello everyone. My name is Yang, and I'm a second-year master student from Dr. Wu Man and Dr. Lia Xiao's group. And this work is based on this paper with Dr. Wu Man. So today I'd like to talk about the dynamic behaviors of black hole phase transitions near quadruple points. Here is our outline. First, I will give you an introduction on black hole chemistry, and then I will talk about the quadruple points in black hole phase transitions. Next, we will discuss about the dynamic processes of the quadruple points. Finally, I will make the conclusion. First, let's go from black hole thermodynamics to black hole chemistry. In black hole thermodynamics, the mass of the black hole M is interpreted as the energy, and the surface gravity kappa is proportional to the temperature of the black hole, and the horizon area A is proportional to the entropy of the black hole. And this is the first law of black hole thermodynamics. The variation of the mass equals to the temperature times the variation of the entropy. And the black hole chemistry is indeed the black hole thermodynamics with cosmological constant lambda. So the main idea of the black hole chemistry is that we identify the mass as entropy instead of energy, and we also identify the cosmological constant as pressure, and the conjugate variable of the pressure is called the thermodynamic volume. And this is a generalized first law of black hole chemistry. So the variation of the mass equals to the variation of the energy equals to temperature times the variation of the entropy minus the pressure times the variation of the thermodynamic volume. So what are triple points? Water has triple points where three phases can coexist. So in water's case, we have the solid, the liquid, and the gas phases can coexist as a triple point. So how about black holes? Can black holes have triple points? Yeah, the answer is yes. So recent study find that black holes can also have triple points. And black hole triple points were found in various types of black holes, including the multi-spinning ADS black holes, the charged Gauss-Blay black holes, and the Labrador black holes. So in the context of black hole chemistry, the different phases of black holes are distinguished and characterized by the size of black holes. So we have the small black hole phase, the intermediate black hole phase, and also the large black hole phase. And how about quadruple points? In chemistry lab, the quadruple points were found in polymers and the colloids. So, and this paper is showed the quadruple point here, where the four phases can coexist. And can we go from black hole triple point to black hole quadruple point? The answer is also yes. So the black hole quadruple points are the points where four black hole phases can coexist. So this paper shows the quadruple point in the black hole chemistry. So we have the smallest black hole, the small black hole, the large black hole, and the largest black hole can coexist in this quadruple point. So based on this paper, this is our setup. We consider the four-dimensional Einstein gravity coupled nonlinear electron dynamics. So this the action of our theory is given by this expression. The first term is the Ricci scalar term, the Einstein-Hilbert action term, and the next term is the cosmological constant term, and the third term is the nonlinear electron dynamics term, where the F mu is the electromagnetic field tensor, and the alphas are the coupling constants. And by varying the action, we can get the Einstein-Paul-Maxwell equations. The first equation is the Einstein equation. So the left-hand side is the Einstein tensor, and the right-hand side is the stress-energy tensor for the electron dynamics. And the second equation is the generalized Maxwell equation. And by considering the following ansatz, describes a spherically symmetric static black hole, where the vector potential is given by this expression. This yields the below field equations. So when we use the power series expansion method to solve these field equations, we can get the the black hole solution here, we can get the solution for the C's and B's, which are determined by the mass M, the charge Q, and also the coupling constants alphas. And to find a black hole quadruple point, let's focus on a setting in which the alphas are non-zero and the independent for I is less or equal than 7. So in this case, we can have the solution for the phi's and Q. And we can check that if all the alpha i's for I is greater than 1, as it should be 0, we can recover the ADS charged black hole solution. And so for this solution, we can compute the thermodynamic quantities. We can compute the entropy, which is proportional to the area of the black hole horizon, and also the pressure, which is proportional to the minus cosmological constant lambda, and also the computed variable of the pressure is the thermodynamic volume. And also we can compute the Hawking temperature and the equation of state. So the equation of state, we meet it in chemistry, which is a relationship between the pressure, the temperature, and the volume. And so, after getting these thermodynamic quantities, we can study the quadruple points in the black hole phase transitions. So, in the context of black hole chemistry, we can compute the Gibbs field energy, which is the entropy minus temperature times the entropy. So, by plotting the Gibbs field energy versus temperature, we can get this diagram. So, in this diagram, the 4 blue lines are the 4 stable black hole physics. This is the smallest black hole, this is a small black hole, and this is a large black hole, this is the largest black hole. And we can find that there are 4 black hole physics and also 3 swallowtails. And by adjusting the parameters, by adjusting the pressure, the charge, and also the coupling constants alphas, we can make the 4 blue lines intersect at a single point. So by adjusting these parameters, we can make the previous diagram become this. This is still the Gibbs field energy versus temperature diagram. But in this figure, we can see that the 4 blue lines intersect at this single point. So this point is the quadruple point, where the 4 physics can coexist. So also in this temperature range, we can find that the 4 black hole physics are permitted. And to understand the dynamics of the black hole phase transition process, we need to introduce the offshore Gibbs field energy. So the offshore Gibbs field energy is a function of the horizon radius at various ensemble temperatures. So instead of using the Hawking temperature here, we need to introduce the ensemble temperatures. And so this is the offshore Gibbs field energy. And by plotting the offshore Gibbs field energy versus the horizon radius, we can get this diagram. In this diagram, as we can see, there are 4 local minimum corresponding to 4 stable black hole physics, and there are also the 3 local maximum corresponding to 3 unstable physics, and all the other points on this curve is called the transient states during the black hole phase transition processes. And let's look at the 4 stable black hole physics. As you can see, this is the smallest black hole, this is a small black hole, and this is the large black hole, this is the largest black hole. And if we change the ensemble temperature a little bit, we can see the different structures of the offshore Gibbs field energy. In cold temperature, this is the blue curve. So in the cold temperature, as we can see, the smallest black hole has the lowest Gibbs field energy value, while the largest black hole has the highest Gibbs field energy value. So the smallest black hole is preferred in this case. And for the hot temperature, the red curve, we can see that the largest black hole has the lowest Gibbs field energy value, and the smallest black hole has the highest Gibbs field energy value. So in the hot temperature case, the largest black hole is favored. And if we adjust the ensemble temperature to make these 4 local minima have the same Gibbs field energy value, so this is the temperature that corresponds to the quadruple points, where the 4 black hole physics has the same Gibbs field energy value. And this figure shows the ensemble temperature, the different ensemble temperature in one figure. And so we can talk about the dynamic processes at the quadruple point. After introduce the optional big field energy. To understand the dynamics of the black hole phase transitions, we need to use the Small-Chomsky equation, which is essentially the diffusion equation under some given potential. So in this case, the optional big field energy GL plays a role as a potential, and the role of PR is the probability for the system to be stayed in the black hole state with horizon radius r at tiny t. And the d here is the diffusion coefficient, and the beta here is the inverse temperature. And to solve the differential equations, we need to introduce the initial conditions and the boundary conditions. For the initial condition, we set the initial state to be some Gaussian wave topic picked on one of the four stable physics. So the initial state can be the smallest black hole, or the small black hole, large black hole, or the largest black hole. And then for the boundary conditions, we set the respective boundary conditions at the true size of the optional fixed field energy. So low probability current can escape from this potential. By solving the Small-Chomsky equations numerically, we can get the time evolution for the probability distribution function. For example, this figure shows the time evolution for the probability distribution function at the middle temperature. So it is at the quadruple point temperature. So as we can see, this figure, this direction is the time direction, and this direction is the horizon radius direction. So this means the smallest black hole, this means the small black hole, and this is the large black hole, this is the largest black hole. And the z-axis is the probability. So as we can see, if the initial state is the largest black hole, at time goes by, the probability for the initial largest black hole will decrease, while the probability for the other three states will increase. So this means that the probability will diffuse from the initial largest black hole to the other three stable physics. So this means that black hole phase transitions can indeed happen. And so how about we change the initial states? If we change the initial state to be the large black hole, we can also observe that the probability will diffuse from this initial state to the other three physics. And also, if the initial state is a small black hole, the probability will diffuse to the other states, and also for the initial smallest case. So for all the cases, we can see that the black hole phase transitions can happen. So now let's focus on the probability time evolution for the four stable physics. So the four curves here means that the probability for the four stable physics. The blue curve is the probability evolution for the smallest black hole, and the red curve is the probability time evolution for the small black hole, and the orange curve corresponds to the large black hole, and the purple curve corresponds to the largest black hole. So in this low temperature case, we have this optional fixed field energy. So in a cold temperature, we find that the smallest black hole has the lowest fixed field energy value, so it is the preferred state. So as we can see, for these four cases, regardless of the initial state, we can find that after a sufficiently long time, this probability will become stationary, and we can find that the blue curve wins, so the smallest black hole wins. That means that for the final stationary state, the system will have the most probability to stay at the smallest black hole case. So this is the same as we predicted here. And for the high temperature case, so in the high temperature case, we have the red optional fixed field energy. So in this case, the largest black hole has the lowest fixed field energy value. So the largest black hole is favored. So let's see the time evolution for the probability distribution function. If the initial state is the largest black hole, you can see that the system will remain to be the largest black hole because it has the lowest fixed field energy value. But if the initial state is the large black hole, or small black hole, or smallest black hole, we can see that finally the purple curve will still become the dominated one because it has the lowest fixed field energy value. So finally, the largest black hole wins. The purple curve has the highest probability. And if we adjust the temperature to make it just right under the quadruple point temperature, this means that we have the black curve where the four stable physics have the same Gibbs free energy value, so there are no preferred states. So as you can see, after a sufficiently long time, regardless of the initial state, so the four black hole physics will have the same final stationary probability, so they merge together. So in this case, the four equivalent physics coexist, we cannot distinguish them. So now let's make a conclusion. First we find the black hole multi-critical points, and then we study the phase transitions at the multi-critical points, and we found that the phase transition can indeed happen. And we also analyze the dynamics for the phase transitions. We find that initially the probabilities will diffuse to the other three states. And this means that the black hole phase transition can indeed happen. And finally, we found that the probability distribution will become stationary, and the final stationary probability is determined by the optional Gibbs free energy. This is our references. So that's all. Thank you.
Hey, do you have any questions for John?
I have one. So it looks like when you increase the temperature or decrease the temperature, you go kind of from this flat line with all the minima to a monotonically increasing or monotonically decreasing case. So it either favors the largest or the smallest black holes.
Yes.
Can you, is there some way to choose the parameters such that either the small or the large black hole is preferred, or is there some intuition as to why that would never be the case?
Yeah, thank you for your question. In our study, we find that when adjust the temperature, either either the largest black hole or the smallest black hole will be favored. But we didn't observe the phenomenon that that is not monotonically. So yeah, we didn't find that phenomenon.
Do you think it would be possible, or probably not?
Probably not.
Okay.
This was very interesting, even though I don't know anything about black holes. These phase transitions, can we think about them as first order phase transitions? Do they have like a latent heat associated with them? Is that, maybe this is a naive question.
Yes, the phase transition is actually the first order phase transition, because if you look at the Gibbs free energy versus temperature diagram, you can find that the first order derivative is not continuous.
Mm-hmm.
So it's so you're right, it's indeed a first order phase transition.
I had a question. So these were series solutions, right? Or asymptotic series solutions?
Yes.
So when you're calculating, determining whether something is large or small, the area that's an approximate horizon, is it?
No, it's exact. So we have different horizon radius and have different the area.
Okay, but wasn't the whole solution an approximation? Maybe I didn't understand something. It was these series solutions. I thought they, yeah.
Yeah, this is just the series solutions.
Can I comment? The solution is exact.
Yeah.
You have nonlinear electrodynamics theory, which in principle can have infinitely many coefficients. But you find if you truncate the series and choose the coefficients in a certain way, then you can get power series, but they're finite in 1 over r.
So they're finite series.
Yeah, they're finite power series, and they are exact solutions to the NLED.
Okay.
Most NLEDs, like Born-Infeld, would have an infinite power series.
Yeah.
But what's there is finite, so everything is exact. The metric is exact, the series are exact, all that stuff.
Thank you. We have time for like one more question.
Can I ask a follow-up? Could you potentially get second order phase transitions and criticality and all the stuff that goes with that, or is that not possible?
Maybe that's possible, but we didn't study this. Maybe we can do it later.
It is possible, yes, but as she said.
Alright.
Okay, let's thank you very much.